Welcome to Stuy Splash Week 4. This is the presentation on control theory reinvented for FRC. Um, yeah, and thank you for everybody who can come. I know some of the SE newbies will be here. Um, just an overview of what this presentation is going to be. I'm first going to go over some basic context of the Limelight, which is going to be used in a couple of the examples. Then a super simple overview of PID and things to look out for when making your own control loop. How to interpolate values of the Limelight with encoders in the gyroscope and why it's very important to do that, why robot tipping is really bad, and how we can reduce tipping and other cool things we could do with that information. To start, who am I? I'm Sam. I'm the Vice President of Software Engineering for 694. In 2020, I wrote the drivetrain/control code, a lot of the Limelight alignment and autocode, and a significant amount of the shooter code and the PID loop for the shooter. I have about 4 to 5 years of Java and C++ experience, and I'm also really passionate about mathematics and physics. And you'll see that that's a significant part of this presentation. All right, so to start off with the Limelight. So the Limelight is basically a super simple camera. It shoots green light out, and the retroreflective tape of the target will illuminate and show the target to the camera. What the camera sees is something a little bit like this. The bright green light can be easily filtered out, and you can draw a little box around it. And from that, we get the angle of the target, which can actually give us a lot of information. Um, this is so the angle of the target horizontally is obviously important because you want to make sure um, you're aligned correctly when you shoot. But you can also get the distance based on how high or low the target is, because you know the height of the target. So this will be important later, but we can get the distance of the target and the angle of the target through the Limelight, which is extremely important. So PID control. Uh, so you guys have probably heard of PID control. I'm assuming that a lot of you guys might have an idea of what it is, but basically what PID does is it takes in an error and it gives you a resulting speed to reduce that error. So like moving the robot at that speed will reduce the error. Say, I'm going to share this. Basically how it works is it notices that it's behind where it should be, so it starts to move forward, or like it starts to turn towards the target because it notices that it's too far to the left. And here's an example of a super basic PID alignment thing that we whipped up in a couple seconds for Destiny when we still had access to the lab. Um, yeah, that's what that looks like. So what's the P in PID stands for proportional, and this is the part that moves the robot towards the target. If you're further behind than where you should be, it'll try to move you forward. And if you're like too far forward, it'll try to move you backwards. So here's a proportional versus time graph. As you can see here, the the it starts to oscillate because it moves too fast, and that means that the p-value is too high or that you're moving too quickly. And so you can either reduce the p-value, or we can get into what next thing is the derivative. So basically what the derivative is it says not only if I'm ahead or behind the target, but it also takes into account the current speed of the robot and predicts where the robot will be. So here we have like the purple line, right? Which basically shows a prediction of where the robot will be in 1 second. And as you can see, it's sort of shifted to the left a little bit compared to the yellow line. That means that it's accurately predicting where it's going to be in the future. A bigger derivative means you predict further into the future, and the robot will slow down more as it gets closer to the target. And a smaller derivative means predicting less into the future, which means that it'll become more and more like a P controller. But this creates an issue. Well, one more example of a derivative. Here, if you have like a simple sine wave, and you take the derivative of that sine wave, you're going to get a cosine wave. And here, if you add that to the sine wave, you can see it gets shifted a bit to the left. So this is very important because robots have momentum because they have mass, so they're going to have momentum, and a robot can't immediately change speed, so it's going to need to take its current speed into account when trying to reach a certain target. Um, but this creates an issue because when we try to do this with the Limelight only runs at about 20 frames per second, while the robot updates at 50 frames a second, which means that the robot's not always getting uh, recent information, which can create a prediction which looks a little bit noisy. And let's zoom into this and see what's going on. As you can see, the Limelight is only updating the position every other tick, which means that the derivative every other tick is 0, and then the derivative, like, on the other tick would be, like, some high value. So here you could see that the robot's predictions are extremely volatile, and this can be really detrimental to a PID loop and, like, outright cause it to fail. So, how do we fix it? In 2020, we didn't necessarily have the most amount of time to fix this, so we put what's called a low-pass filter on it which basically averages the past few values and smooths it out a little bit. And it worked okay, but it was far from perfect, and it created a little bit of a noisy signal, as you can see here, but it was significantly better than what was going on beforehand. Um, what is a low pass filter? Well, this will be covered in the second half of this presentation, but this next part is what I think is the most interesting. Oh, and also a side note about PID. We had created a automatic PID tuner. It was based off I can't really pronounce that. These two guys created a automatic PID tuning algorithm that worked actually really well for our shooter and our like angle alignment. But we didn't have enough time to research this as much as we wanted to. But the data that we did collect showed that it was fairly effective for how convenient it was to use. Um, Encoder interpolation. Now, this is the most interesting thing that I think that we ended up doing in 2019. So, as explained before, the Limelight runs at 21 hertz and the robot updates at 50 hertz, which means that for a lot of ticks, which are these red bars, it's going to return the same value as it did in the previous one, which, as demonstrated with the derivative, can be detrimental to the effectiveness of your PID loop. So, yeah, without accurate recent information, it's going to be nearly impossible to align with the target. So, what could we do about this? What we can do is use the encoder. So here's a couple of terms that I'm going to use. The base truth is the values that we know are correct. Every time the Limelight gives us a new value, we know that is where the robot was, or what the robot was doing, and we can assume those are correct. The other type of value is the encoder/gyroscope values. We know that these are accurate to what's going on, but we don't know that they are exactly correct. They update really quickly, however, they may drift over time, and it's important to check in with the base truth to make sure that your encoders aren't drifting or your gyroscope. So, and also interpolation or prediction. Using a combination of both the base truth and the encoder values, we can get a roughly accurate prediction of where the robot is currently, and this vastly improves the effectiveness of the robot because this is going to not only give us extremely quickly updating values, but it's also going to give us accurate values. Because when we just smoothed it out before, right, it's hard to see here, but when we applied the filter to it, it can't generate new information. So it created a latency. So while it did improve the um, it it improved the performance of our system. However, it was not perfect, and it did cause some oscillation due to the latency that it, like, put in the system. Um, so also here, so we know that the encoder values are related, but they might not necessarily be aligned. For example, here you could see the encoder values are related, but they're not the same as the Limelight values. They are sort of offset. So we're going to need to also take that into account in order to accurately combine the two. So what's the plan? So when the Limelight turns a new value, assume that is where the robot is right now. The Limelight does have some latency, which is caused by the network latency and processing latency. But for the most part, that is kind of negligible, and the issue of repeated values is significantly more important. Um, when the Limelight does not return a new value and returns the old value, get the change in the encoder value since the last Limelight update and add that to the base truth. That way we can get where the robot currently is um, and have the best of both worlds. We can have the accuracy of the Limelight and the frequency of the encoder updates, meaning that the issue of a noisy derivative is pretty much gone, which greatly improved the performance of our PID loop. So there's a couple of issues with this, but it's mainly regarding our team 694 because we are significantly behind in the use of encoders, to be quite frank. We don't use them to their full potential, and there's room for significant improvement here. We still take the absolute value of both of the encoders just in case one of them doesn't work, but this causes a lot of issues. For example, if the robot were to turn to the left, although it might not have moved forward, the way we have our encoder set up would report that if we were to turn, our robot would be moving really quickly forward. So we can't use the encoder values for too long because the way that we program them, at least, has some significant issues. But if you were to say take the average instead of the absolute value, a lot of these issues would go away. So where else do we use this? We use this with the NavX, which has a gyroscope on it. So in between the frames of the Limelight, we can also use the gyroscope to get even more recent values, um, uh, which made it significantly faster, the alignment, and was a great improvement. It removed a lot of the stuttering, and but this only applies if your robot, like ours, moves the entire robot to align with the target. A lot of robots have turrets on them, unless the turret has its own gyroscope, which I'd find kind of unlikely. Uh, you wouldn't like you'd have to the gyroscope would have to turn with your robot for you to interpolate the Limelight values with your gyroscope. How do we implement this? So basically, the way that we did it is our PID loop was entirely encoder driven, except the target encoder values in the control loop would be periodically updated with information from the Limelight. This is a bit of code that's a little bit hard to describe, but you can go to our GitHub and look at our code. And if you have any questions, you can always like type it in the chat, and I'd be happy to answer it. Um, so tipping. Tipping is a pretty big issue with our robot this year. As you can see, our Limelight right here is at the top of the robot, and the robot is kind of top heavy. It's not as top heavy as it was uh, in I think it was the year before this one, our robot Alfred, which was extremely top heavy. This one still tips though when it accelerates, and tipping is particularly a bad issue in the robot because the way that we get distance is based on the pitch, which is basically the angle upwards. Um, and so if the robot were to tip, it would think that the target is moving either really far forward or really far back really quickly, which can cause the robot to make some like very dangerous movements if it's trying to align with that. Um, so like the tipping, especially in the PID loop, causes even more tipping and even more problems, and it's really something that you should strive to avoid. So how did we reduce tipping? Again, this video right here, it's not necessarily easy to tell, but we did have to reduce, like we had to reduce the amount of tipping in the robot. As you can tell, the robot is sort of slowly accelerating and slowly decelerating. And that's not a issue with the robot. The robot can actually accelerate quite quickly, but through algorithms, we intentionally slowed it down to reduce tipping because even more than Edwin, this robot here, Destiny from 2016, tips quite a bit, which made the Limelight alignment quite difficult. So how did we reduce tipping? We used filters, which is something that I put a ton of work into last year and actually won us an Innovation and Control Award in Palmetto, which I was really happy about. So as you guys are probably aware of the coronavirus, a lot of the coronavirus statistics actually take a 7-day average of the cases as they fluctuate depending on the day of the week. So what this does is we have a sequence of values, be it the number of coronavirus cases that day, and we filter it, say the average over the past 7 days, right? And that's just one of the filters that we use in robotics called the moving average. And there's quite a few other ones that we use. But that's just sort of what a filter would be. It's basically a way of taking a sequence of data and like modifying it to get more use out of it. So a lot of this information is going to be in our tech binder where I put where I wrote a lot about filters, especially on our GitHub and our tech binder. I put like a ton of effort into documenting these well, but I'll give a brief overview for the sake of this presentation. Um, so because of this, I won't be showing the code because I feel like the code is oftentimes confusing, but if you are interested enough, you can always go look for yourself and there's comments all over the code. However, if you're still confused, you can always shoot me a message and I could put my email in the chat if you guys are curious. But so what's a rate limit filter? Yeah, also I did give a presentation last year about filtering, but that was a significant, it was pretty old information and the research that we did on filters has significantly changed it. So the rate limit filter is the standard one, the standard ramping filter built into WPILib. It's not amazing at reducing tipping or power consumption, considering the amount of control that you lose. A lot of the times, these filters have these advantages such as lower power use, better consistency, or less tipping. They come at the cost of having less control over the robot. So the rate limit filter isn't really a great balance between the two. It's you lose a lot of control considering the amount of reduction in power usage you get. So it's easy to understand and implement. It limits the amount that it can change over time, but it's not as amazing as it could be. The best filter by far, by a mile pretty much, is the low pass filter. This one is pretty much used everywhere in our code and used for pretty much everything, including the smoothing out driving controls, smoothing out the data in that we get from the Limelight, smoothing out like the information that we send to the motors. It's what's described as a rule of thumb filter, meaning that it should be tried first because most likely it's the filter that you're looking for. The way that it works is a little bit complicated, but you can always go on Wikipedia and check the mathematical description for it. It basically, you'll see it's like it exponentially decays towards the like input value, sort of smoothing it out. Yeah, this one is super great. We use it for everything, and it's pretty much the most used filter that we used by far. A moving average, as described like before with the COVID-19 data, takes the average of the last few values. It can be really good at smoothing out noisy values and especially looking for trends. For instance, if recent values are lower than than the average, that means that it would usually be going down, and if recent values are higher than the average, it means that it could be going up. Because of this, a moving average is often used in stock trading to determine the trend of a stock, um, whereas like the low pass filter isn't as good at detecting trends because it's not really aware of trends. It only takes in like the most recent values, whereas this one has the context of the past few values. However, for taking in Limelight data where more recent values are important than older values, or driver input, where again, you're going to want the robot to respond quickly, uh, this one has some serious disadvantages. It's really only good in non-real-time situations, which isn't that common in FRC. So the speed profile is it was sort of a failed experiment. It algorithmically removed a jerk from a signal, which would theoretically reduce tipping. However, the delay that this filter caused was so severe that drivers would oftentimes lose control of the robot because this initial acceleration was extremely difficult to notice, and the driver would try to speed up more and more while it was still accelerating, and the robot would end up going way faster than expected. Uh, Again, we also didn't have that much time to test it, but this one doesn't seem to be as useful as we were hoping for. So why is the low pass filter so good? The low pass filter is an extremely fundamental mathematical function, and because of that, its properties are also extremely fundamental. It's extremely good for real-time applications in which the most recent values need to have the most weight in the filter. So whereas other filters take into account past values, say like averaging the past 10 days, where they're all weighed the same, a low pass filter prioritizes the values that come in initially, which makes it really good to use in real-time applications like driving the robot or smoothing out motor values or even taking in like data from like a noisy signal. Uh, so the conclusion, this presentation went a little bit faster than I was expecting, but I mean, considering that we started late, I'd say maybe that's a good thing. But the conclusion, uh, control theory is extremely complicated. A simple PID loop can be really easy to throw in, and it's really easy to botch these solutions, especially if they're quickly put together. And if we leave those solutions in the robot, they can cause particularly difficult issues to troubleshoot down the line. Control theory is super vast, and there are so many rabbit holes to fall down in, and Wikipedia is your friend here. It's really important, though, that before you go on your Wikipedia journey, looking through all the different control theory Wikipedia pages, which are pretty interesting to read, especially if you implement them in your robot, that you understand a couple of the mathematical symbols. Because before you learn calculus or some of the weird notation that they use, it can be really hard to understand what they're talking about. So, um, yeah, that concludes the control theory presentation. I guess in the YouTube chat, they could put like questions, and then Ian could put them in the Zoom chat. And if there's no questions, I guess that's the end of the presentation.
We have one question from before. Will you post these slides somewhere?
Um, yeah, sure. I'll put the slides, I can put them in the Slack channel or, let me just, I'll put them in the YouTube chat.
Also, this recording will be posted on our YouTube channel, so you can reference that at any time.
Alrighty. So, yeah, I guess that's it. If there's no other questions, then, yeah, that concludes the presentation. I guess I'll just stop sharing my screen now.